Hey everyone, welcome back. Today we're going to be studying one of the topics that is crucial to your understanding of linear algebra as we go forward. So we'll start with a definition. So let's let V be a vector space. And then I need some vectors, so let's call them V1, let's say, and let V1 up through V sub k be vectors in V, right? So we start with a vector space, and then we've chosen these vectors right here. An expression of the form A1 times B1, so constant or scalar times B1, plus scalar times B2 plus dot dot dot, plus scalar A sub k times B sub k. This has a special name. It's called a linear combination. We saw this definition earlier, so linear combination. We saw this definition in the context of matrices and especially in terms of column vectors. Now, what we're doing is generalizing this. Anytime if we have a vector space and a collection of vectors, we can form an expression like this, and that's called a linear combination. So, for example, let's say in R3, here's an example of a linear combination. 2 times the column vector 1, 1, 1, plus 4 times the column vector 1, 1, minus 1, minus, or let's say plus negative 2 times the vector 0, 0, 1. There's an example of a linear combination. So there's nothing really exciting or difficult going on here. It's just scalar times vector plus scalar times vector plus scalar times vector. And I wrote 3 of them out here. There's nothing special about doing 3. I could have done 7 of these, right? The 3 here does not correspond to the number of vectors that I'm using here. And let's do another example. So, in P2, remember P2 is the vector space consisting of all polynomials of degree less than or equal to 2. And so here's another example of a linear combination. How about 3 times the polynomial 1 plus x squared plus negative 4 times the polynomial x plus 3x squared plus, and I guess I'll put a 1 here, plus, I mean, it looks kind of funny, but just to be consistent here, 1 times the polynomial 1 minus 2x squared. All right, so there's an example. Yes, I did 3 pieces again. There's nothing special about the 3. It's just constant or scalar times vector plus scalar times vector plus scalar times vector. All right, so those are examples of linear combinations. Now, here, this I would say, if you want to rank the importance of definitions, this definition right here, when it comes to linear algebra, is in the top 5 in terms of important definitions. All right, linear transformation is one of them, vector space is one of them, and this one I'm about to write down right now is also one of them. So, let's let V be a vector space. And let's let S equal to V1 up through Vk. So what we have is a vector space, and then we have this set S consisting of the vectors V1, V2, V3, all the way up to V sub k. The set of all linear combinations involving vectors, or involving the vectors V1, V2, up through vk. So we do all possible linear combinations that you could ever create using the vectors from S. This is called, so this is the span of S, and it's denoted span, so nothing fancy here, span parentheses S, right? So that's called the span of S. So this is a definition that takes a little time. You got to wrap your head around. So what we're doing is we start off with this collection of vectors, and then we are going to consider every possible linear combination that you can form. All possible linear combinations. Now we're going to work with this concept of span constantly for the rest of this class. And so here's the first sort of, let's say, important fact. So let's call this a theorem. So let's let S equal to V1 up through Vk be in V. So what we have is we've got this subset of vectors that live inside the vector space V. So part A, the span of S is a subspace of V. So that's exciting. What this tells us is every time we choose some collection of vectors living inside V, we can create a subspace by considering the span of that set. Right? And then part B just sort of elaborates on exactly what this subspace looks like, or gives us some characterization of the subspace. So if U is a subspace of V, so if we happen to have some other subspace of V, and S is contained in V, in U. So if all the vectors in S, so V1 is in U, V2 is in U, and so on. So if U contains all the vectors from S, then span of S is contained in U. So if you have, let's just kind of draw a picture. Well, let me draw a picture over here. So let's say our vector space V is here. We've got a subspace U here, and U happens to contain, all right, let's say there's V1 and V2 and so on. If it contains the space, if it contains each of these V's, so V3, here I did it with 4 of them here, then it contains the span. Right? Now, and a way to think of this, what is this actually saying? It's saying, or a way to interpret this, the span of S is the smallest subspace that contains each of those V's. So we can say that in parentheses. So, span of S is the smallest subspace of V containing S. Right, so there's a way to think of what span is. And I actually want to prove this, all right, to get a little bit of help in working with this definition. So for part A, let's see, I need to show that it's a subspace, and so how do we do that? Well, we use the technique that we learned last time called the subspace test. So it goes like this. See, now what do I need to do? To apply the subspace test, I need to show that the set is non-empty and that it's closed under addition and scalar multiplication. So note, or let's say since each v sub I lies in span of S, right? Remember, the span of S is a set of all possible linear combinations. In particular, it contains the linear combination that has only a 1 times vi and 0 times all the other vectors lies in the span. So since each vi lies in the span, we see that span of S is non-empty. Okay, so we've got the non-empty part out of the way. Now I need to show that it's closed under addition and scalar multiplication. So let's choose a couple of random vectors inside span. So let's let x and y be in the span of S. All right, so what does that mean? So that means that x, well, let's see, if it lives in the span, that means that it is a linear combination of the v sub I. So x looks like this, a1 times v1 plus dot 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 plus a sub k times v sub k. Of course, now the lights just went out on me. There we go. And y is equal to b sub 1 plus dot 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 plus b sub k times v sub k. If you live in the span, then you are a linear combination, so you have to look like this or this. So now, if I look at x plus y, if you add those together, here's what you get. a1 plus b1 times v1 plus dot dot dot. A sub k plus b sub k times b sub k. What is this? This is a linear combination of the v sub i's. Constant times v1 plus constant times v2 and so on. So this, let's say, and if I look at, say, r times x, that's going to be ra1 times v1 plus dot 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 plus r ak times v sub k. Okay, here's another linear combination. So both of these lie in span of S. So by the subspace test, span of capital S is a subspace of capital B, closed under scalar multiplication and under addition. Now to prove part B, I guess I'll do that over here. So let's see, what do I need to do? I need to say if we've got some other subspace that contains each of the VI's, then it contains all of span S. So for part B, suppose each V sub I lies in capital U. Now, remember, capital U is closed under scalar multiplication and under addition because it is a subspace. Right? So, it follows that any expression of the form A1 times B1 plus dot 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 plus A sub k V sub k. What am I doing here? I'm doing scalar multiplication and then I'm adding all of this lies inside V. So of this form lies inside U. U is closed under scalar multiplication and under addition. Well, so what are we saying then? All possible expressions of this form lie inside U. Well, what is span of S? It is the set of all possible expressions of this form. So it follows. That span of S is contained in capital E. Okay, so that completes the proof. Let's just look at some examples now. In fact, I want to do lots and lots of examples involving this concept of span. And what you really want to do, or what I hope will happen as we continue discussing this idea of span, at some point you'll get a feel for what it means, and in particular, what span looks like. So let's start with this example. In R3, let's let S be the following collection. So I want S to consist of two column vectors. The first one is 1, 0, 1. That's a 0 there. 1, 0, 1, and 0, 1, 2. Now, what I'd like to do is try to get a feel for what the span of S looks like. Right? Well, who is this set? Well, so now span of S is the set of all linear combinations of this form right here. So it'll be something like a constant 1, let's just call it A times 1, 0, 1, plus some other constant. I'm going to use a B here, so constant B times 0, 1, 2. Okay. All possible linear combinations. Take all those together, that's the span of S. And if I join this together, let's see what I get. I get vector A here, B, and A plus 2B. So the span of S is the set of all vectors that look like this. A, B, and then the last entry, A plus 2B. Now, what I want you to notice, so let's say note, any such vector solves the equation and the equation is x plus 2y minus z equals 0. So any vector of this form right here, take the a, put it in for x, take the b, put it in for y, and take a plus 2b and put it in for z. All vectors of this form satisfy this equation. And if you remember back to Math 143, what does this equation define? That defines a plane in R3. That is what the span of this set looks like. Remember, the span is a subspace, and what subspace is it? It is the plane given by that equation right here. So we can say, span of S is the plane in R3 through the origin with normal vector (1, 2, -1). And let's actually try to draw this picture here. So let's see, my first vector was 1, 0, 1. 1, 0, 1. So it's something like that. And then the second one, 0, 1, 2. Something like that. So there's the two vectors, there's 1, 0, 1, and there's 0, 1, 2. And so the span, what you want to do is imagine if you extend this out like this and out like that, and this vector out like that and out like that, the span is the plane that contains these two vectors. All right, so it's hard to draw this, but it's the plane that contains these two vectors. The normal vector right there is the 1, 2, negative 1. So in general, we'll just kind of put this off to the side. So in general, in either R2 or R3, if you want to get an idea of what span looks like. So in general, in R2 or R3, span of a single vector is a line. Now, why is that? Right, so in either R2, I guess I'll just draw it in R2. If you take a single vector and you look at all possible linear combinations, well, what did that mean? So if this is my vector v, all possible linear combinations are things of the form a times v. So all possible scalar multiples of v, what do those do? Right, they go like that with positive scalar multiples. They go like that with negative. And if you take all possible scalar multiples, it fills out that line. So span of v is a line, and span of v1, v2. So if you have two vectors, as long as they're not parallel, as long as they don't lie on the same line, so the span is a plane. Okay, so let's look at some more examples. So next example, in Rn, let's let S equal, we've seen this before, this is what we call the standard basis for Rn. It's the vectors E1, E2, up through E sub n. Remember, E sub I is the column vector that has zeros everywhere except in the ith spot. Right. So let's take the standard basis vector for Rn, and let's just look at the span. So then, span of S, so what's that going to look like? Well, it's all possible linear combinations involving these vectors right here. So right below, I'm going to write the answer here, so we're going to identify who the span is in a second. But let's just think about that. So that's going to be an A1 times 1, 0, 0, plus A2 times 0, 1, 0, plus blah, 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 down to A sub n times 0, 0, 0, 1. Okay. So the span is a set of all possible linear combinations like this. And if we join this together, what's this equal to? A1, A2. So as a single column vector, that's what it looks like. So the span of S is the set of all vectors that look like this, where I can put anything I want for A1, anything I want for A2, all the way down to A sub n. So, well, what are these vectors? This makes up all of Rn. The span of the standard basis is Rn. Every single vector in Rn can be expressed as a linear combination of these vectors, because every vector in Rn looks exactly like that. As a second example, in P sub n, remember that's the set of all polynomials of degree less than or equal to n, let's let capital S be the following polynomials: 1, x, x squared, and I want to go all the way up to x sub n. If we look at the span of this set, so I've got the polynomial that's just the constant polynomial, the 1, then the degree 1 polynomial x, x squared, and so on. a typical vector in the span of S looks like. So let's see, what does it look like? It looks like an A0 times 1 plus A2 times X plus A3 times X. Oh, no, sorry. I got my subscript screwed up. That should be an A1 there. That should be an A2 there. All the way to A sub n x n. So a random vector, if we chose something in the span, it looks like this. Guess what? Every polynomial looks like this. So what does that mean? A conclusion. Span of S is equal to P sub n. So notice what we've done here, these last two examples, we had situations where I took a certain set and I looked at the span and I got the entire vector space, right? In this case, I got all of Rn. In this case, I got all of Pn, right? So that's an important idea. When this happens, in fact, we give it a name. So let's say definition. If span of S is equal to V, we call capital S a spanning set for V. So under this terminology then, what we have is E1 up through E sub n, that's a spanning set for Rn. One x squared all the way up to x to the n, that's a spanning set for P sub n. Right, so this leads to a couple of important questions. A couple of them. So the set goes like this. Let's take, so let's let S be some collection of vectors. So let this be a subset of vectors in some vector space V. So we've got some set S. The first question you want to ask, what we'd like to be able to ask is, given some vector, let's call it little u in capital V, does little u lie in the span of S? So there's one question you might want to ask, right? We have this set sitting inside V. We know that the span of S is some subspace of V. So if we choose a vector u at random inside V, does it lie inside the span or not? Right, so the picture, here's V, here's the span. And if we chose some vector u, can we decide, does u lie inside the span or not? All right, so there's question number one. And then question number two is S a spanning set for V. These questions are actually related, pretty fairly closely related, right? Does the span, is it actually some smaller portion of V, or does it actually fill out all of V? Now, when this happens, right, when we have a spanning set, here's the viewpoint that you want to have. A spanning set gives you building blocks for creating all of V. So let's write that down. So when span of S is equal to V, so when S is a spanning set for V, we can view the vectors V1, V2 up through Vk as building blocks I'll put that in quotes here. We can view it as building blocks for V. And why is that? Well, what it means, if the span of S is equal to V, then any vector here can be constructed by making a linear combination using these V's right here. So that's what I mean by the building blocks. How do you build them? By forming linear combinations of these vectors. Okay, so as the first example, let's work in R4. So in R4, let's let S consist of the following vectors of 1, 0, 1, 1, and 3, minus 1, 0, 1. So here's our set S. And then the question is, does the vector 2, 1, 1, 1 lie in the span of S? Right? So this is connected, or this is an example of answering question number 1. Okay, so how do we answer this? Well, the answer will be yes, if this vector 2, 1, 1, 1 can be expressed as a linear combination of these two. And the answer will be no if you can't. So the solution goes like this. We try to solve the following equation. A times 1, 0, 1, 1 plus B times 3 minus 1, 0, 1 equals 2, 1, 1, 1. Okay. So if we can find an A and a B that satisfy this equation, solve this equation, then we'll say yes, this vector lies in the span. If there are no such A and B, then we'll say no, it doesn't lie in the span. Okay. Now, this actually converts. I can rewrite this as a linear system, right? In fact, there's a corresponding augmented matrix that looks like this: 1, 3, 2, 0, minus 1, 1, 1, 0, 1, 1, 1, 1. Right? So we can convert this equation right here into the following augmented matrix. And if we do some row operations, so let's see, I've got a leading one there. I'm going to turn these down here into zeros. So this will be a 1, 3, 2, 0, minus 1, minus 1, 1, negative 3, no, sorry, 0, subtract, negative 1, and 0, subtract, so that's a negative 2, negative 1. And then the next step looks like this: 1, 3, 2, 0, 1, 1, 0, minus 3, minus 1, 0, minus 2, minus 1. I just multiplied, I don't know why I do this, but I multiplied that second row by negative 1 just to make it positive. And then, so here's a leading 1 now. I want to clear out the these entries right down below. And so I'll get a 1, 3, 2, 0, 1, 1, 0, 3, 0, 2, and 0, 0, 1. Hey, check this out. We've got a row right there consisting of zeros followed by a 1 at the very end. So what does that mean? It means that the system is inconsistent, right? It's telling us that 0 plus 0 plus 0 plus 0 equals 1. Right, so this is inconsistent. Which means that the system, the original system, has no solutions. There are no A and B for which this equation holds, and so the answer is no. That vector does not lie in the span. There are no A and B that solve that equation right there. Okay, let's do one more example. And this will be another example of question 1. Or I guess answering question 1. So let's see, this will be in P3. In P3, let's let S consist of the following polynomials: 1 plus x and 1 plus x squared. All right, so there's a couple polynomials. And now the question is, does the polynomial 1 plus 2x minus x squared, 1 plus 2x minus x squared, lie in the span of S? And here's the answer. One plus 2x minus x squared is equal to 2 times that first polynomial, 1 plus x, plus negative 1 times 1 plus x squared. That's just not. Oh, yeah, that's right. So we have 2 minus 1. Yeah. And then I have 2x, and then I have minus x squared. Yeah, so if you check, this equation is true. Sorry, I got tripped up there for a second. And so what does that tell us? It tells us that this polynomial right here can be expressed as a linear combination of the two vectors that we have in S, and the answer is yes, it lies in the span. We expressed it, yes. We expressed our polynomial as a linear combination of the vectors in S, and the answer is yes. Okay, that's a good place to stop. What we'll do next time, we'll pick up with addressing this second question, right? Do we have a spanning set? If we have some set S, can we identify it as a spanning set or not?